the whiteboard discussion for experiment number 10. This one we do not have a video. When Dr. Fusco and I went through them, we decided not to do a video of this one, so you're missing out on a few things. But what this lab is about is we're using spectrophotometry, and actually what we do is we determine how much blue dye is in red raspberry Kool-Aid, which is kind of cool. It's very easy to do. Now, spectrophotometry is an analytical technique, and it's a very common analytical technique. And what's nice is it's very non-invasive, meaning you don't destroy your sample at all. What we do is we use light. Use absorbance of light for analysis. And you've done this yourself, you just can't be quite as quantitative. You could have two solutions that were blue, and one is bluer than the other, and you could say this one is bluer than that one, but you can't say how much. So what this does is it takes advantage of what's called, the machine can do the how much. It takes advantage of what's called Beer's law. Now most people think Beer's law is a 2 at 10 is a 10 at 2, but actually that's not the case. Beer's law is absorbance is epsilon B C. So A is the absorbance of light. So when light is absorbed, it moves electrons between energy levels or whatever. Epsilon is called the molar absorptivity. And it is a physical property of a substance. It's how much light it absorbs per mole per liter. And it's usually a very big number. And that's important because if this is a big number, that means you can measure absorbances. You can measure absorbances. And if this is a big number, that means this can be a really small number. B is the path length. It's the distance through the sample that light travels. It's typically held constant. And then C is the concentration. So it's molarity, or parts per million. All right? And as I said, what's nice about this technique is A, it's non-invasive, and B, let me just clean this up a little bit. It's non-invasive because you're literally just shining light through it, and so you can just use the sample again. And also, it's very sensitive because since this is a really big number, if this is a small number, just to put it in perspective, we can measure absorbances at 10 to the minus 2 and get good accuracy. If this is, say, 10 to the 6th, that means this could be 10 to the minus 8th molar, and we could still read it. So that's very, very sensitive. Now, because these two in a thing are held constant, typically we go A is Kc, that's supposed to be an equal sign. And so what you do is you measure, where can I do this? You do knowns and unknowns. So what you do, let's do it over here. Keep going back and forth, Rob. You can measure absorbances. And this will be concentration, say in molarity. And you measure a bunch of knowns. And in your case, you're going to do 2, 4, 6, 8, 10 times 10 to the minus 6th. I'll explain how you're going to do that. And you'll get values. And typically you get very pretty lines for stuff like this. Beer's law plots are really nice. You draw your best line. And then you take your unknown sample. In this case, maybe a sample of Kool-Aid. And you go, oh, the Kool-Aid absorbed here. Therefore, the molarity must be there. Reading it right off the graph, just like what you did in the density lab. All right? So I'm going to go through how you're going to do this in a minute. Before I do that, there's a picture in the lab manual. Let me show you how these instruments work a little bit. So, and this is a nice picture in a lab manual of this. So they typically have like a light bulb, light source. That's a bad light bulb. And then that light bulb will hit something like a prism or a diffraction grating, and it breaks the light up into its component wavelengths. Red, orange, yellow, green, blue, violet. That goes up against a barrier, and the barrier has a little slit that goes through. This light is called the incident light, I0. Then it goes into your sample. This is called the transmitted light. And then this goes to a detector. Which is like a photocell. All right. The ratio, let me erase some of this. So the instrument knows, and by the way, this distance here is B. This is the path length up here, right? So the instrument knows, the instrument will know I0, and so then it measures I. The ratio of I to I0 is called the times 100, excuse me. Times 100 is the percent transmittance. In the old days, you had to do the math. Nowadays, we have computers. Absorbance is the negative of the logarithm of the transmittance. This is, all right, and so the instrument does this calculation for us. But just realize that anything that prevents light from getting to that detector, the machine doesn't know where it went, it just thinks it's absorbed. All right, so things like bubbles or fingerprints or things like that can really screw things up. All right, now let me go through what you're going to do experimentally, what you would have done experimentally and where the data comes from. Let's make this, let's stop here and I'll make this whiteboard video 1, and then we'll have whiteboard video 2 for this. We'll have 2 whiteboard videos.